Welcome to video 13.2 in our first Principles of Astrophotography series. In this video we discuss the conditions needed for diffraction-limited imaging called lucky imaging.
Lucky imaging is used to obtain astonishing diffraction-limited detail on small, bright objects like planets.
This video is based on section 13.2 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility.
This is an amazing image taken of Jupiter by Daniel Dress using lucky imaging. It's just incredible what you can do. If you compare this with what you can see through the eyepiece, looking at Jupiter, even at moments of good seeing, you can't see anything like this. And so it's a way of just extracting just an incredible amount of detail out of your telescope. In a lot of deep sky imaging, the aperture doesn't matter that much, but in lucky imaging, it matters a lot.
Yeah.
And the reason is, the bigger the aperture, the bigger the diameter of your main lens or mirror, the smaller the little airy patterns are going to be, the smaller the little airy discs are going to be, and the more detail you'll be able to see. So this particular image is taken by an EdgeHD 14 by Daniel Dress.
For diffraction-limited imaging, focal ratio is f between 3.5 p, and that's the pixel size.
In microns.
In microns, and 7.1 p, pixel size in microns, are well sampled. Oh, right, where p is the pixel size in microns, lower values are undersampled and higher values are oversampled, with the critical focal ratio equal to 5 times the pixel size.
That's right.
Being critically sampled.
That's right. So the focal ratio is the ratio of the focal length to the aperture. And that's a dimensionless number because the focal length is typically measured in millimeters. The aperture is typically measured in millimeters, and the millimeters cancel, you get a dimensionless number for the focal ratio. But pixel size is not a dimensionless number. It has dimensions. It's normally measured in microns. And so this formula mystified me the first time I ever taught it, and a lot of astrophotographers were talking about it. You just take your pixel size in microns and you magically multiply by 5, and that gives you the ideal focal ratio.
And they got 5 from
out of the air.
Yeah.
It seems seemingly out of the air. But where they got it is this calculation that we're about to do.
Okay.
So I'm sure, because this is really the only way to do it. So we're going to show you where that 5 comes from, if you've ever wondered about that. To start off with, we have the formula that we did in the last video, video 13.1, for the critical pixel scale. So that's the size of the sky covered by a single pixel that will resolve all stars in the sky regardless of orientation. Remember, we talked about if the stars are oriented along the axis, the X or the Y axis of the camera sensor, or if they're oriented at a diagonal, this will resolve any two stars in any orientation. That's
Great.
why we call it the critical pixel scale. But what we used in that was the theta I, which is the full width at half max of the seeing. Here we're going to say, no, I'm not limited by seeing. I'm limited by diffraction. I'm going to take such short exposures that all that jiggling around that is caused by atmospheric turbulence, I'm going to freeze it. I'm going to take a picture while Jupiter looks like this, and then take a picture while Jupiter looks like that. Then I'm going to use sophisticated software to put all those images together and extract as much detail out of Jupiter as possible.
But does this doesn't just apply to lucky imaging, though?
No.
Diffraction-limited seeing
Yeah.
is a principle the whole way along.
Yeah. So, for example, if you can afford to get a spot on the Hubble Space Telescope, or you can get on one of Elon Musk's SpaceX journeys, you're above the Earth's atmosphere, take your telescope up there and you can get diffraction-limited seeing as long as your optics are diffraction-limited.
Easy.
So, but the techniques for processing lucky imaging are very, very different, and we have a lot of references in our book if you want to learn more about it. This is just a basic introduction of what the sampling looks like for lucky imaging and where that 5P comes from. And I'm grateful to Andrew Emiet, who helped me write this section, because he's a very experienced planetary imager, and he has a FAQ on cloudy nights that's excellent on this subject. I think you should write a book. So where does this 5 come from? And the answer is, instead of, in the examples we used in the previous video, we said, okay, let's say we got 2 arc seconds full width half max of the stars, and that's our resolution. We're going to ditch that, and we're going to say, no, I'm limited by diffraction. And this is the full width at half max, theta I, limited by diffraction. And that, according to section 8.2 in the book, and I think we put this in video 8.2, but at least it's in the book, goes like 1 over the aperture. The rest of that is just a bunch of numbers on the right-hand side. But the important thing, and we talked about this before, the bigger the aperture, the smaller the area disk. The smaller those stars are in your image, and the better the resolution. The more resolution you can get for the bigger the aperture. That's why this full width at half max of the diffraction-limited area pattern goes like 1 over the diameter instead of being proportional to it. You want the smallest area disk possible. So all we're going to do this calculation is to insert this equation for the full width at half max into that equation for the critical pixel scale. And then we're going to set that critical pixel scale here equal to this stuff on the right-hand side. So let's do it. It's not that hard. First thing I'm going to do is to stuff this theta I in the second equation into the first equation. So the first equation then is going to be PC. I've got a 1 over 2 square root of 2 times theta I. And theta I I'm going to get from the second equation. That's 1.029 times 0.55 millimeters.
Thanks for using your units.
You're welcome. Times 648 arc seconds divided by pi and divided by d. Now I'm going to set that equal to the third equation. This is a lowercase p, that's the pixel scale. This is an uppercase p, it's the pixel size in microns. And this is the focal length. And now we're going to set that equal to this. So this new equation equal to 648 arc seconds millimeters. We're being careful about units here. We're being honest. Pi microns times the pixel size p in microns divided by the focal length f in millimeters. And so what we're actually trying to find is the focal ratio. I want to find the focal ratio. And what's the focal ratio? Well, the focal ratio is the focal length divided by the aperture. That's what I'm looking for. Then what I'm going to do is multiply both sides of this equation by f. We got it over here, we can multiply by f there too. These f's cancel, and that will give me an f divided by d, and an f divided by d is the focal ratio. We just went over it. Okay, so what do we have now? We've got 1.029, 0.55 millimeters, 648 arc seconds divided by 2 square root of 2 pi times f over d.
Great.
Which is big F. And that's equal to 648 arc seconds millimeters over pi microns. Let's see if there's any miracles that are going to help us out here. I've got a 648 arc seconds on both sides of the equation. Am I right or am I right?
Yeah.
I've got a millimeter in the numerator on the left and a millimeter in the numerator on the right.
Lucky you.
Lucky me. I must be living right. And then I've got a pi in the denominator on the left and the right side. Ren is so excited about this. I can see
pumpkin.
it. And then we forgot the p. This p comes along to the right. All right. Now, with all those cancellations, if I want to solve for f, I want to solve this equation for f, then we're going to multiply both sides of this equation by 2 square root of 2 and divide both sides of the equation by 1.029 times 0.55. And that will give us f is 2 square root of 2 multiplied by that. We're going to divide by 1.029 times 0.55 and the only unit that's left over is this micron right here, and then we have a p left over on the right hand side. Alright, that was minorly painful, so sorry about that, but this is where it all comes from. This number, so let's double check our units. When you're doing physics, the first thing you're going to do is check your units and make sure they work right. The focal ratio is a dimensionless number. It better not have any units or you made some kind of mistake. But the pixel size does have units, and it's normally measured in microns.
Yeah.
So when you put in, say, like on our camera, 3.76 microns into here, then the microns are going to cancel.
Right.
And you're up and you're off and running. And this number here is equal to 5.0 over microns, p. So that's where that 5.0 comes from. The 2 square root of 2 just comes from the geometry of critical sampling. 1.029 locates the full width at half max of the airy disk. The 0.55 microns, that came from the average visible wavelength. So the visible wavelengths are between 400 nanometers and 700 nanometers. Halfway between those two is 550 nanometers. That's where that 0.55 came from. But all that boils down to this result where the critical focal ratio is equal to 5 times the pixel size in microns. Where do these numbers come from? Well, the well-sampled range that we defined for regular imaging is that we divided and multiplied by the square root of 2 the critical pixel scale. And so we took this number and we multiplied it by square root of 2 to give theta over 2. For the upper limit, we divide by the square root of 2 to give theta over 4 for the lower limit in the previous video. And when you multiply this 5.0 by the square root of 2, you get 7.1.
Is it actually 5.0? That's not a...
It's 4.997 something or other. It's not exactly 5.0.
Oh, that's definitely roundable.
Let's look at the telescope that Daniel Driss used to take this image. He used a Celestron C14 EdgeHD with a 2 times power mate Barlow, and that Barlow ramps the focal length up by a factor of 2.
Yeah.
So the focal length native of that telescope is 3910. Yeah, it's a lot of focal length, dude. Yeah, multiply that by 2 and you got a heck of a lot of focal length going on.
That's almost 8,000.
The diameter of the aperture is 356 millimeters. He used the camera, used the ASI 664, and a lot of these guys do one-shot color release.
Really?
Yeah. I think for something like this, it doesn't really have emission lines. It's just it's a continuous spectrum.
Oh, yeah.
It kind of makes sense. Why does he use that small pixel size?
He wants to get as close to diffraction limited as he
He
can.
wants to get close to diffraction limited. The smaller the pixel size, the easier you can get there. So then focal ratio is that focal length, 2 times 3910, divided by d, which is 7.6p. So this gives us a focal ratio that's 7.6 times the pixel size. To be well sampled, we need to be between a focal ratio between 3.5 and 7.1.
Just barely
A
oversampled.
little bit oversampled. And maybe his seeing justifies it.
I bet if he would have used the 1.5 Barlow, it would have been on the lower end. So
Yeah, and so it's never going to come out exactly right. You're exactly right. In a conversation with Andrew Amiot, he said that as far as this range goes, from 3 to 7, that if your seeing is bad, then use 3. If your seeing is superb,
Phenomenal,
use 7.
yeah.
And if you're just average seeing, use 5. When you're at 7 or 7.6 in the case of Daniel Driss, you're claiming that you can do better than diffraction limited resolution. And Andrew claims that you can. Thanks so much for watching.
and we'll see you next time.